So my name is Mohit. I am the teaching intern for this class. Dr. Rosini is out of town for a family emergency. So I'll be teaching you this class and the next, and hopefully I'll be teaching you some of the classes in the future, especially buckling. So I think he's teaching Euler-Bernoulli beam theory, and the Euler-Bernoulli beam theory is also referred to as classical theory for beams sometimes, mainly because it's highly fundamental. It has a lot of assumptions, as you would know, but still it is being used in the industry for preliminary design, especially when someone has to do just solve some basic problem involving either bending or buckling. So we'll go ahead and continue the Euler-Bernoulli formulation. I think he taught you that the strain at any point will be represented by three coordinates, x1, x2, x3 in a given cross section. And it's defined as sectional strain minus x2 k3. Does he refer to as k3 or kappa 3? K. Okay. So k3 it is curvature, sometimes referred to as kappa or k, and then plus x3 kappa 2 x1. I think he covered till this point. So this essentially is an expression to evaluate strain at any given point in the beam. You just have to plug in the coordinates x1, x2, x3, and you will be able to evaluate what's the strain. So now, to evaluate stresses, we have a very important law. Can anyone tell me? Hooke's law. So it is based on some assumptions. What are the assumptions? Linear elastic. Isotropic. Yes. Homogeneous. That's important. So Hooke's law, we apply that here. So we essentially calculate stresses at any given point in the beam as E times the strain expression. So this is valid for a linear elastic isotropic homogeneous material. Okay, so if you have taken a continuum mechanics course or a solid mechanics course which was offered last semester, you would know that the material matrix C is essentially E over 1 minus nu square 1 nu 0 nu 1 0 0 0 1 minus nu over 2. This is valid for a plane stress case. Okay, I'll do that. Thanks. So this is valid for a plane stress case. But if we think that the Euler-Bernoulli beam theory is valid, then essentially our theory is valid when mu is much smaller or essentially goes to 0. Right? So a plane stress case, when the Poisson's ratio is going towards 0, it is kind of equivalent to the Euler-Bernoulli beam theory and is in line with the assumptions. Okay, so it's important for us now to evaluate the stress resultants. The stress resultants will help us determine whether the stresses in the beam are something which the beam can take for design aspects or any other solution related aspects. So for a beam, generally it would have two kinds of stresses. The stresses which we talk about in Euler-Bernoulli beam theory, they are essentially axial and bending. So we have one axial direction and we have two bending directions in this problem, right? So I'll draw the stress resultants for you. So the axial one, let's say if this is the beam schematic, the axial stresses would be along the x1. Then there would be bending in one of the directions. Yeah, I should make that. And then we have bending in the third direction. Okay, so we have the expression from here. Sigma is, so this would become your sectional axial component. Then similarly, this would be one of the bending components, and this would be the other bending component. Now, if we have to evaluate the stress resultant, so the stress resultant for the axial component, it is written as N1 of x1. Again, it's a sectional quantity, would be equal to integral over the area of cross section for all the stresses that are on the section. So if I have sigma 1 so at each point on the section, I have sigma 1, x1, x2, x3 as my stress, integrated over the area will give me a stress resultant. So I can substitute the value for the stresses So I just substitute the value of stresses in this expression. And then we just simplify this expression. So we have epsilon 1 bar x1 integration over the area for E dA. This assumes that E may not be uniform. So it's not for a uniform material. Then I have minus K3 x1. I'm taking these terms which are dependent on x1 outside the integral because they are not dependent on x2 and x3, whereas the integration over the area involves only x2 and x3. and then the last term. Is this visible? Okay. So it's important to note that all the integrals, they depend only on the material properties and the geometry. They do not depend on the external loads applied. So for any given problem in which we have a beam cross section and we have the material properties, we can evaluate the stress resultants using this expression. So maybe I can write a note. So all the integrals depend only on material properties and cross-sectional geometry. They are defined for a given beam and are independent of external loads. So this integral here is sometimes referred to as axial stiffness, because if you remember, this entire term is related to axial component of stresses, right? So this is sometimes referred to as axial stiffness. So we will call it S. If E was uniform, if the material was uniform, and we can evaluate the area over the integral for 1, it will become EA, which is commonly known as the axial stiffness. So this is referred to as the axial stiffness. And similarly, the other components are referred to as the bending stiffnesses. Now let's say if we had a layered material. For example, we have a beam in which there are two materials, A and B, and we want to evaluate the axial stiffness for this material. Then we would have axial stiffness as integration over the area for EdA, where area of the cross section belonging to the A layer, and then we will just add for the B EdA. So let's say if we had a layered material of n layers and we want to evaluate the sectional stiffness, it would just be the same, just the summation of all the integrals. And if this cross section is defined in such a way that this is width B and each of these layers are of height hi, then the axial stiffness would just be the summation of I goes from 1 to n E times B EI, because each of the layer could have different modulus. So EI times B times HI. So stiffness is additive, it's an additive property. All the layers, if they are well defined, we can calculate the area and then just multiply with the Young's modulus of each layer and add the entire thing. Okay, so this is axial stiffness S. Now let's evaluate S2. S2 is referred to as the bending stiffness about X2. So it will become and then similarly we have the S3 integral So finally we have the expression for the axial stress resultant. And it can be written in a matrix form. So N1 X1 is equal to a 1 by 3 matrix of S, S3 minus S2, multiplying a 3 cross 1 column matrix of axial sectional strains, the curvatures about X2 and the curvature about X3, sectional curvatures about X2 and X3. So these are sectional stiffness measures as we discussed, and these are sectional strain measures. So let's talk about a short example. So let's say I have a cantilever beam of an arbitrary cross section. So cantilever fixed on the left end, and free on the right end, and I apply a load P, P1 let's say, because it's along X1. So I want to evaluate the sectional stress resultant N1, let's say at some X from the fixed end. So essentially N1X. So what should be the value of N1x. So the sectional stress resultant is essentially stress times the area, right?
N1 is the load, correct?
N1x is the sectional stress resultant. That's
N1 is stress.
it's a stress resultant. So essentially what's happening in the entire cross section, stress is applied at each point. We kind of integrate it over the area to get sectional stress resultant, so it becomes a force, right? So N1x will be equal to P1. Now this problem would have only N1, which is the actual stress resultant, if P is applied at a special point, and that point is centroid of the cross section. If P, the external load, is not applied at the centroid of the cross section, it would induce some moment stress resultants also, which would lead to some bending. So for that we shall look at what's a centroid and how can we evaluate a centroid of a cross section. So for an arbitrary cross section, let's say our coordinate frame is attached to an arbitrary point O with x2, x3 as the sectional coordinates. Our centroid would be somewhere, let's say that the point is C. So the coordinates of the centroid x to C would be equal to 1 over S integration over the area for Ex2 dA, which becomes S2 over S, and then X3C is going to become 1 over S integration over the area Ex3 dA, which is going to become S3 over S. Yes.
Like, you have N1x one there, and then you have N1x equals P1, but isn't x that point, like, that's like halfway down the beam?
Yes.
So
I'm evaluating N1 at location X.
Yeah, why is it P1?
Because it's a axial load which is applied at the centroid.
Okay.
So essentially, if you cut any cross section in the beam, then you have a free body diagram, let's say for this portion. So this is the cut, and I have P1 here, and I have my N1x here.
Okay. Okay, I understand.
Right? So through equilibrium, N1x is P1. But that is valid only at the centroid, so the centroid is evaluated in this manner.
So that's how you find that's how you find the coordinate of
Right.
x2 centroid?
Yes, because x2 and x3 are the cross-sectional coordinates.
Yeah.
So the cross-sectional coordinates for the centroid x2c and x3c are defined in this way. It is essentially a sectional average of the stiffness measures. And of course, if I didn't mention, S is equal to integration of E dA.
How did you derive the equations for the coordinates of the centroid?
So you can do this by taking small element over the cross section, and then you just have to add all those coordinates for that cross section. So if you take an infinitesimal point, you have the distance of this infinitesimal section from this point O, and then you kind of sum all of them and take the average. So S is essentially EDA. So if you add everything in the cross section and then take an average about EDA.
So is that the bending moment equal to 0 and then derive the equation?
No, it's nothing to do with bending moments. So for example, center of mass. What you do is essentially add all the masses and their locations and then divide it by the total mass you have. So similarly, you have a cross-sectional area here and you have the coordinates, or how far is it from a given origin. So you essentially kind of are averaging the material you have at a different location.
Right. But okay. Got it.
Go ahead. Yeah.
No, but how do you get Young's modulus in the equation?
Okay.
If you only constrain the area.
So for example, if I have this continuous body and I have a small infinitesimal area, let's say I call it dA, and I know that the modulus of this infinitesimal area is E. So what I have is E times dA at some location x2, right? So I have all the materials in this cross section which are located at some x2 if I look at only one direction. So I will, for addition of all those areas, I will just integrate it over the area, and then I take average with the material I have, right? So this gives me only one coordinate, x2, and then I get the x3. It's an analogous to the mass center. So now if our origin was the centroid, then x2 and x3 go to 0, and essentially x3c and x2c become 0. So if the origin was the centroid, then x2 and x3 of the centroid would be 0. Okay, so let's, so far we talked about the axial components, axial stress resultants. Let's talk about bending. So if there is a beam, if at a random point or arbitrary point I have a load applied or stress present, sigma 1, at an infinitesimal small area dA, then my moment sectional resultant m3x1 becomes negative of sigma 1 x2 dA. Understood? If you are looking from x3, this stress sigma 1 is going to cause a clockwise moment. So negative integration of over the area sigma 1 times x2. x2 is this distance, which is the lever arm for the moment, and times dA integrated over the area. So we have the expression for E1, sigma 1, and we get minus epsilon 1 bar x1 integrated over the area Ex2 dA minus K2 x1 integrated over the area Ex2 x3 dA plus K3 x1 integrated over the area Ex2 square dA. So this is S2, which we characterized before in the actual stress resultant problem. I'll refer this to as H23. Again, I'm not taking the e's outside the integral because it may or may not be uniform. And then this is H22, or actually it's referred to as at H33 because this is about the x3. So this is inertia about x3. So just simplifying this expression becomes minus epsilon 1 bar x1 s2 minus k2 x1 h23 plus k3 x1 h33. So it would be good if you follow these notations for the sectional inertia h23 and h33. They will remain consistent throughout the course and with your textbook. Similarly, we can write the moment m2x1, the sectional stress resultant for bending, about x2, and that will be integration over the area sigma 1 x3 dA. No negative sign because if you look from x2, this sigma 1 is going to generate an anti-clockwise moment, so positive. Integration over the area sigma 1 x3 dA. x3 again is this distance, so the lever arm for that moment. So it can similarly be written as integration of E x3 dA times epsilon 1 bar x1, which is the sectional axial strain, minus k3 x1 integration over the area E x2 x3 dA, which is the H23, plus k2 x1 integration over the area E x3 square dA, and this term now is H22, which is the sectional inertia about x2. So let me write the axial stress resultant again. It's so now we have the axial stress resultant, which is the N1 x1 then the two bending stress resultants. So we can write them in a compact form. So we would have a column matrix of n1 x1, m2 x1, m3 x1. Yes. And we have a column matrix of the sectional strain measures. So these are again sectional stiffness measures these are the resultants. Okay, so now let's say we are operating at the centroid. So our O is the C, O is the origin, C is the centroid. Then S2 will become 0, S3 becomes 0. Why? Because they have integration E x2 dA over the area over EdA. x2, if it's the centroid, it becomes an odd function, so the integration goes to 0. Similarly for x3. Right? So if we are evaluating this sectional stiffness measure over the centroid location, then we would have S0000, H22 at the centroid, H23 of the centroid, so the sectional stiffness measure will become, we can evaluate S, we can evaluate H22, H23 if we have the cross-sectional geometry and the material properties. So we can evaluate the resultants.
In what case does it become that?
It will become this if we are operating on the centroid. So H22C, the superscript C, is the H22 evaluated at the centroid. So the values will differ based on the integration and the values of x2 and x3 when the centroid is the origin. Okay, so now as you've seen in the example, that when we had external applied loads, we could evaluate the actual sectional resultant, right? But we don't know the strains. That's what one of the unknowns are. So we will calculate the strains given the sectional resultants. So we need to invert this relation, right? So after inverting, this relation becomes column matrix of the sectional strain and curvatures will be equal to 1 over S. This can now be used or inverted in a block manner. 0 0 0 0. And then the column matrix of the sectional stress resultants. Where delta H is just H22C, H33C minus H23C whole square. So we did this so that we can evaluate the unknowns, the strains and curvatures, the sectional strain and curvatures, and eventually we will substitute these values in the expression for stresses so that we can evaluate this actual sectional stresses, right. So this will become, these are the actual stresses we are evaluating. So this is the expression for the axial stresses. So this relation provides the link between the stresses and the applied loads, which are the N1, M2, M3, the M2, M3 in this expression, right. Again, if we have, let's say, a symmetry in the cross section, right now this expression is for an arbitrary cross section where the loads are applied at the centroid. Even if the loads are not applied at the centroid, you can always evaluate them at the centroid, right. Just movement of forces, like a force when translates, it adds a force and a moment. So this expression is for the stresses evaluated at a cross section, or actually evaluated at any point in the beam when the origin is the centroid, but there is no symmetry. If we have a symmetry, about x2 or x3, it's important, or x2 or x3, H23C will become 0. Why? Because H23C was basically integration of the area with E x2 x3 dA. So the power of x2 and x3 is 1. If any of them becomes an odd function, the integration goes to 0. I'm assuming you know what is an odd function. It is essentially something like this. So antisymmetric about the origin. So integration over this domain goes to 0. So similarly, if x2 or x3, any of them becomes an odd function, means the cross section has symmetry about either x2 or x3, this integration will go to 0. So h2 3c becomes 0. So our sectional stress resultants will become the sectional stiffness matrix times the strains and curvatures, and these h2 3 terms will go to 0. So this becomes a diagonal matrix. It also means something else. It means that the bending in one direction will not cause bending in the other direction. So in this problem, or in this expression, the bending, the two bending and the axial components, they all are decoupled. So to solve a problem like this, you can just have one equation each for one deformation mode, axial bending in one direction, bending in the other direction, and you can just solve this problem. You don't need to take care of the coupling between the directions. So we had this expression for the axial stresses in which h2 3 was present, means it's for a case where the section is not symmetric. Now when the section becomes symmetric, we will not have these terms, right, and delta h is h22 times h33. Again, this goes to 0. So you can cancel them, and essentially you will have sigma 1 E n1 over s plus x3 m2 over h22 minus x2 m3 over h33. So we'll cover till this point in this class. I'll move out of your way. If you have any questions, you've got 1 minute. Okay.